Hello, hello, hello. I forgot I'm live, but I'm posting to Instagram, so give me 1 second, people. I'm gonna just. Well, that photo's horrible, but who cares? Mm, yeah, it's not making it better. Let's just stick with no filter. Okay, and then uh, reversing a linked list live. Reversing a linked list on my first try. And then let's grab. There's no way this is no copyright. That's crazy. Um, hello, hello, hello. Sorry, I'm just posting to Instagram, so give me 1 second. Dum 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 dum. Dum 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 dum. Okay, I'll just maybe while I do this, I'll start talking a little bit about. So yeah, hello, welcome back. To myself because I've been on a week hiatus apparently, unplanned week hiatus, but yeah, I just okay. Just last week was a little bit weird. We had that holiday on Monday, um, and then I was pretty busy that week, so I was just like, I'm gonna take a break, just for this week, gather up, and then start back up again this week. So that's what I did. But I was missing it, so we're back, and we're gonna do some LeetCode. I have 3 streams this week because also like last week I had four. Also, I was pretty tired, and I had that LeetCode contest at the end of the week. Which I mean, you might have seen in the post if you're here from LinkedIn, but I will be doing another LeetCode contest this Saturday. So that'll be fun. Okay, let me not put that on the microphone so I don't get copyrighted. Okay, well, whatever. Um, so yeah, I wanted to get back to this, and now we are. I'm gonna do some LeetCode today, and then on Thursday I'll be back and I'll continue working on the agents project. See if I can get a little bit ahead of that. And then on Saturday I'll be doing another weekly LeetCode contest, same time at 10:30 start, but I'll be a little bit earlier at 10. So that'll be fun. But yeah, no, my last week, I mean, we had the holiday on Monday. I watched, I think that was last week, right? Yeah, it was the third. I watched Spider-Man on that Monday. Did I not stream that week? Huh. I watched Spider-Man on that Monday and just like work. I don't think I did anything special. This weekend I went to the beach in Barrie. It was really nice with a couple of friends. And this week back to work. Whole week. This is my second day. I work from home today. Um, but yeah, I'll nothing. I don't know. I've been learning a couple things at work. Oh, something cool. That I learned at work that maybe I'll talk about later. I don't know. Do I want to get into it? I learned about um content addressable storage, which was kind of cool. Like a coworker mentioned it to me, and I looked into it, and it's an interesting way to store files. It's used by Git, and it sort of fixes a problem with like when you're storing files when you care about this, and that is if you store the same file twice, if you're using like just like a regular, like let's say MongoDB in like an S3 bucket and you're referencing it there, if you store the same file twice, if your user attaches the same file twice, you're basically like having double space for no reason. Imagine if you do it 3, 4, 5 times, you're wasting space and it's not being efficient. And sometimes you want to have those copies because sometimes the user wants to have multiple copies of their same files. So sometimes it doesn't matter. So for example, for Google Drive, this doesn't matter because you can upload the same file to multiple folders or even to the same folder. And you want to keep all those different copies because maybe you need them for some reason. But there are some other cases in which when you upload the same file, you shouldn't have the file twice. And it should just be like, oh, I already have this file again. Don't upload it again. Don't waste those resources. One such example is Git. Git, if let's say you delete a file and then you add it again, it doesn't like create a new file that it's tracking. It recognizes that it's the same file and then it just like keeps track of that same file. How does it do this? Through hashes. And like hashing is important when you're trying to establish like a read-only like architecture. So in Git, it's not like it's like read-only. Like you can modify files, but for each revision, each commit, you don't want that file to be modified in the commit. Like once you make a commit, that file, whatever its contents were at the point of the commit, should keep static. It shouldn't be changed after the fact. So what you do is you use hashes to identify like a version of a file, right? So when you commit that file, you make a hash of its contents, and that hash is like a certificate that identifies that a file hasn't been changed. So let's say, for example, I changed that file. When you check the hash of the changed file and of the file at the point of commit, you're gonna see that the hashes are different. So you're gonna like understand that there's a difference between the two files, right? You don't want to, especially because Git doesn't keep like it's not like a backup. It's not a backup. It keeps like changes between files, but it doesn't keep like whole files. So you need a quick way to be able to compare if a file has been changed. In this case, it's an object, like it's not only files, but let's just talk about files in this case. And so that's what this content addressable thing is. It's basically like if I'm uploading the file twice, you identify it by its hash, and you don't like add two files. You just overwrite the previous file, or like you don't even upload it at all. Right? So for something in my project, I need to do something with files, and I need to be able to reuse those files for further runs. It's a matter of scale. Once you like system gets big and big and big and big enough, you don't want to be like reusing like creating duplicates of files and stuff like that. So that's why this was interesting in this use case. And then I learned another thing, which was directory hash based sharding, and it's another thing that Git does. In fact, maybe let's look at that for a second. So I'm gonna let's just open like some repo I have. Let's open my LeetCode repo, right? So there's this .git folder. If you go into objects, you see all of these, right? And if say you're like, why is there just like a letter and a number? Like you can identify, you might be able to identify that this is hex. So if I open any one of them, you'll be able to see here like this is a hash, right? This is like the commit hash that you have. I don't know if this is a commit. This is just an object, so it might be something else. But you know the commit hashes that you have. These are these files identified by their hash, right? And so what's the reason why we have this 2A, 2C, and all that stuff? The reason why is that what this represents is basically the first 2 bytes of is it 2 bytes? it's a letter from it's a character. I don't know if you store it in bytes, but it's basically 4 bits, right? Like a single, yeah. So the two of these are, yeah. This is 1 byte actually. Each hex character is 1 bit. Sorry, 4 bits. Yeah, because you need 16, right? So 2 of these is a byte. So you're keeping like a byte of the hash, the first byte of the hash. You're keeping that folder here, right? And so the whole hash of this file is not 3. It doesn't start with 3, 4e, whatever. It's actually 2c and then 3, 4e, blah 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 blah. We're just keeping the first byte as a folder so that our file like our file management system doesn't get overwhelmed, because if we just had every single commit just in the top level directory without having these folders, when you're loading it and searching through it, it makes the system very slow. Maybe not in this project, because I maybe don't have that many commits and work trees and all that stuff, but when you get like a lot of commits, then if you just have them all in the parent folder, it's gonna take a lot to be able to go into that folder, ls it, look through it. So separating it into different folders makes it a lot faster, but you're just using the first byte. So this gives us like a total of what is it, 256? Yeah, because it's a byte, right? So it gives us 256 possible possible folders, right? I think it's 2 to the 8. Not 2 times 8, 2 to the 8. Yeah, 256. So it gives you 256 possible folders here, and then you go into the commit. So that's a nice way to distribute it. It's a nice thing that I learned. But yeah, anyway, talked a little bit about everything. I should probably just get into it. Let's just go into our Lorcana card of the day. Okay, so for today's Lorcana card of the day, we're reviewing a set 1 card. It's called Work Together. It's a 1 cost inkable action that whose effect it's a sapphire, so blue. That the effect is chosen character gains support this turn. Support, the effect is here. Whenever they quest, you may add their strength to another chosen character's strength this turn. And it says patch up, put your whole back into it. Cusco, this is my whole back. This is my whole back. It's by artist Bill Robinson. It's card 165 out of 204 of set 1. And it's a common. I mean, just reading the artwork, this brings back good memories of The Emperor's New Groove. I really like that movie. But however much you like the movie doesn't really come into play on how competitive it is. And in terms of competitiveness, this card sucks. Giving support to a character, I mean, okay, this could be nice. I can think of 1 deck, but you don't actually really need it. And that deck is let me see. There's a Mulan, a green Mulan. This one. Green blue plane. Okay. I think this is the deck I'm thinking about. Yeah, Ranger plane. So this deck, so this Mulan, whenever its character quests, you gain lore equal to her strength to a maximum of 6 lore. And so what you do is you basically, with support, you give her a bunch of strength, and then you quest for 6, which is crazy. Then there is the Alice, but I don't think the Alice is here. I don't know if it went out of rotation. And then there's this ranger plane. Chosen character with 10 strength or more gets +3 this turn. So that's the support here is very useful. Also with this gadget hack wrench, your characters with support get +1. So support here is very useful. So you use that support to give strength to your other big characters. And then you quest for a lot, basically. I just don't know. I mean, if you get the ranger plane, that just solves it because your characters gain support. But there was used to be an Alice that does the same, and also like it's pretty much the ranger plane. We had like a character Alice. I don't know if she went out of rotation. She might have. Um, so in this deck, that card might be good. Like work together because you can give support this turn to something. But honestly, you don't really need it. Like you already have the ranger plane, which gives support to everything, not to just one character. And then you have characters that just have support, right? Which I don't see a lot of here, so which is kind of weird. I guess you're just relying that you're getting the ranger plane. But yeah, this character gains 4. Yeah, I don't know. This is weird, but yeah, you just basically like give support to something, but like you already have enough characters with support, enough like you have that item that gives support in blue, so this doesn't really come into play that much. If you're playing maybe like draft, it can be good, but this should, and if this is in draft, this should have chosen character gain support this turn, draw a card, because there's a lot of those that just kind of like replace themselves. And then it makes it kind of worth it, but otherwise, like just giving support to a card, it's not worth the space in your deck, right? So those are my thoughts for this card. And with that being said, let's no. Okay, weird. Okay, so we're gonna continue solving Grant 75, and today we're doing reverse linked list, a very, 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 and I emphasize, very popular problem. I remember doing this in, I think I probably did it in my data structures class. I had to reverse a linked list for the first time, so that was nice. So it's just, I mean, it's obviously a linked list problem. I'm just gonna create the solution here, 206.cpp. And then we're gonna grab this, and we're gonna paste it. Okay, it says 206 reverse linked list. Given the head of a singly linked list, reverse the list and return the reversed list, right? Okay, I didn't see this follow-up, but we can do both. I'm gonna start with iteratively because it's the first way I learned it, but we're gonna write both solutions, okay? And so, what is a linked list? Let's go over that first. Okay, let's see examples first. You have this list, and you basically, we have 1, 2, 3, 4, 5. You turn 5, 4, 3, 2, 1. You have 1, 2, and then you turn into 2, 1. The number of nodes is in the list in the range 0 to 5,000, and then blah, blah, blah. Okay. So a linked list is a data structure where you have a node, and then you have a pointer to another node, and then you have a pointer to another node, and so on and so forth, until you have the last node that has a pointer to nothing, in which case it has a pointer to null, actually. It's not that it doesn't have a pointer, it has a pointer to null. And so what is this useful for? What is this useful for? You would say like, oh, well, in this case, we're storing a list of numbers. Why don't we just use an array? Like, why don't we just do 1, 2, 3, blah, 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 n, right? The problem with an array is that to store n numbers, you need n consecutive memory spaces, right? So when you're storing this whole list, it's not that you can, like, let's say your memory looks like this. It's not that you can store the 1 here, and then the 2 here, and then the 3 here, and then let's say you have more memory here. You store the 4 here, and then you can just keep your list like that. No, they have to be contiguous spaces. So if you're storing 1, 2, 3, 4, you need to literally go 1, 2, 3, 4. Now, most of the time, this isn't a problem, but in some cases, your list becomes so big that it's impossible to allocate that much memory contiguously, but you might have that same memory spread across your computer, right? So let's say you want to store a list, and this is your memory. And so let's say you want to start that same 1, 2, 3, 4, right? But in here, you have, you're storing something else. Let's say you're storing a string that says hello, right? So you can't just store 1, 2, 3, 4, because then you would overwrite this H. This H is already taken. You shouldn't be able to do that. So you store 1, 2, 3, and then you can't store anything else if it's an array. If you're storing in an array, because it has to be contiguous memory locations. That's a property of the array, and the reason for this property, in case you don't remember, is that if you remember, if you're trying to access any element in the array, it's O of 1, right? You can just access it instantly, and why you can do this is because you have the way arrays work is you have a pointer to the beginning of the array, and then you have like a metadata, you have like a list of how many elements there are and what size each element is. So if, say, you want to access element 6, you take the pointer to the beginning of the array, and then you multiply 6 times the size of int, in this case, because we're storing integers. And then you move you find the 6th item by adding this plus the location of your pointer. So you add 6 plus that, and then you can basically just access it instantly, because it's all contiguous. That's your assumption. It's all contiguous, so you can access 6 positions later by just doing math, right? You can just calculate the address where it would be, and you know it's going to be there. But if you're using a linked list, we're not storing all of these elements consecutively. We are storing them. Oh, I didn't mean to do that. We can store them in separate locations, right? So I can store 1 here, then let's say I can store 2 here, and there's a pointer to there, and I can store 3 here, and there's a pointer to here, and let's say I store 4 here. And so I don't need to actually store them in contiguous memory locations, or they don't even have to be in order in the memory at all. I can just store them in wherever I want. And this is helpful when we don't have that contiguous space. Another reason why it's helpful is if you want to add an element to this array, like let's say your array is n elements long, or like the size of your array is n, and you want to add another element to here, then you have to resize your whole array, because you already allocated n space, n elements for your array, but then you're trying to store n plus 1. So then you have to basically just allocate a new array with n plus 1 elements, right? And if you're doing this repeatedly, this is like a very expensive operation. Also, if you delete an element from the array, like let's say 3, then you have to shift down all of these elements. You have to go and shift all of these down. And that's O of n. It's also a very expensive operation. If you insert an element in the middle, if you insert an element here, then that costs you also O of n. Because you need, or like let's say if you insert it at the beginning, you have to shift all of these down. So that costs you all of n. O of n. So adding elements to your array in the middle, removing them from the middle, it's an expensive operation. If you're doing from the ends, it's fine normally, but from the middle, like if you're removing from the end or adding to the end, it's like technically it's O of 1, it's very easy, but if you're removing from the beginning or adding to the beginning, then it's a more expensive operation. So there's all of these problems with arrays that most of the time don't matter, but in the times that do matter, you need an alternative. That alternative is linked lists. So let's review a little bit about how linked lists work in these scenarios. So we already mentioned that we can store them in non-contiguous memory locations, so that's one advantage. Second advantage, if we're gonna add an element in the middle, we can basically just like add said element. So let's say we want to add a 5 here in the middle, so we just do 1, 2, and we switch this pointer to be 5, and then the pointer of 5 is going to be 3, and then 4, right? So you're actually like adding it in. You don't have to allocate more memory, you don't have to shift the elements down, you just have to change the pointer. So it's technically O of 1. There is a problem here, and that is you have to find the location where you want to put that element, so that, and I'm going to explain that in a second. Same with you removing them. If I'm removing this element, then I just do the reverse operation. I remove it, and then I point this to this, right? It's O of 1, basically, technically. Problem. With arrays, we established that we could retrieve any of the elements in O of 1. We just do some math and then calculate the address where the element might be, is going to be, and then we just get that element. If we want to get element, let's say 3, normally we have a reference to this beginning of the list. We can't just instantly just go, oh, I know where 3 is, and then access it. Can't do that. Or let's say you want to get the 4th element. Can't just like, oh, I know the memory location and just point at it, because the memory locations are not contiguous. You can't make any assumptions on where it's going to be. So there is where you lose a little bit of efficiency, because you have to actually like walk the linked list until you find your element. So if you want to find the 4th element, you start here and then you go 1, 2, 3, 4. So that takes a little bit of time. It takes 4 operations. If you want to find the last one, it takes n operations. So it's no longer an O of 1 lookup. And same thing if you're inserting, like you have to look up where you're going to insert. You have to walk until you're where you're going to insert and then insert. So it's a little bit more expensive. But like you can, for example, if you're adding or removing from the beginning, it's not O of n like it is in arrays, right? Because, you know, in arrays you have to remove this and then shift everything down. In linked list, you just remove it, remove this, and then you're done. You don't have to do anything else. You don't have to shift them down or do anything. So yeah, that's a little bit of an explanation of what linked lists are. Now reversing a linked list. To reverse a linked list, reversing a linked list is basically you have 1, 2, 3, 4. You want to reverse all of these links back. So 4, instead of 3 pointing to 4, 4 points to 3. Instead of 2 pointing to 3, 3 points to 2, and so on and so forth. So instead of having 1, 2, 3, 4, you want to have 4, 3, 2, 1. That's reversing a linked list. It's a simple to understand problem. The implementation is a little bit tricky, but we're gonna attempt it, right? Okay. So when you're working with linked lists, let's do the iterative solution first. When you're working with linked lists, like like I said, you don't have like array locations, and you can say like the second element, you just have pointers. So normally we only keep one pointer to represent the data structure, and that is the pointer to the head of the linked list or the first element. And that is how we represent the linked list. We just keep a pointer to this, and then since we have this chain, we have the whole data structure represented. Now, how do we reverse a linked list iteratively? We're gonna have two pointers. We're gonna have a current pointer, and we're gonna have a previous pointer. And at the beginning, actually, the previous pointer is not going to be itself. The previous pointer is going to be null. Right? Your current pointer is going to be your head, and your previous pointer is going to be null. Because the previous... actually, this should be prev. And this is going to be null. Because you're saying that the previous node to 1 is nothing. It doesn't have a previous node because it's the head. And now, here is what you're gonna do. So, you know, you have to reverse the link. So a naive operation you might do is just, okay, cur, you call this link next, the next element, so the next pointer. So cur.next is equal to prev. So you basically, what you do is this. Right? And you're like, okay, that's a good step. You've reversed the first link. There's a problem here. The problem is you've lost access to the rest of your linked list. Like, you can't access this element anymore because you don't have a pointer to it. It's become lost in the sauce. Therefore, you can't just like switch it because then you lose access. So before you actually do that switch is correct, but you're missing a step in between, is you keep a temporary pointer that's going to point to cur.next. So you say temp is equal to cur.next, and you point something there to keep a reference to it. Now, I'm going to write down the operation. So temp is equal to cur.next. Now you can do your switch. So cur next is equal to prev. Then you can, so now what you've done is this, right? Now you can switch, not switch, but cur can become temp. You can, oh, no, sorry, you can't do that. That's why I said this is tricky. You have to be very thoughtful about how you do it. Let's say I do what I did. So let's say I move cur to be here instead. Now I have lost reference to this element right here. I can't access it anymore because null doesn't point to here. I have no way of accessing it. So before I actually do that, I have to say prev is gonna be equal to cur. So then I'm moving prev here. And then I'm losing this pointer. And now, so I'm saying prev is gonna be equal to cur. And now I can move cur to temp. Cur is equal to temp. So then now I move this here. And see, now I have access to this chunk, and I have access to this chunk. And now I just repeat the same operation. Let's go through it. Temp is equal to cur.next. So I remove this from here. Temp is now here. Cur next is equal to prev. So this link is now pointing to here. Prev is equal to cur. Okay. Remove this pointer to be here. And now cur is equal to temp. So I move cur here. and I've kept reference to all of my elements. Let's do it one more time. We're gonna do it until we finish the linked list. Temp is equal to cur.next, right? Cur.next equals prev. Prev equals cur. And then cur equals temp. And we do that one more time. So temp is going to be equal to cur.next. Cur.next is actually no. So we put temp here. Okay. Now cur.next is equal to prev. Now prev is equal to cur. And now cur is equal to temp. Now, this is where we can stop. Our whole linked list is reversed. So our condition to stop, if you noticed a second ago, what I did was I moved cur to temp. So our condition to stop is that cur equals no. So while cur does not equal no, that is my condition to stop. And another thing we have to do is right now head is here. Our head of our linked list has changed. Where is our head of a linked list? Prev. Prev is our head of a linked list. So head is equal to prev. And it's done. We've reversed a linked list. Right? And if you've noticed, this should also work in case the linked list is empty. So in case the linked list is empty, head would be null. And if head is null, when we do, at the beginning we do cur equals to head and then prev equals to null. Since cur is going to be equal to null, we skip this, and then our head is going to be equal to prev, our head is going to be equal to null, so this is also going to work for that case. So let's do it. Okay, so we do list node cur, and I think I have to do this prev, and then here cur is going to be equal to head, prev is going to be equal to null, while cur does not equal null. I think I have to do null. Or actually, I think the C++ correct way is null pointer. It doesn't actually matter. I think they're equivalent. Temp, we're going to create a list node temp, which is going to be equal to cur next. I literally just have all the code behind me, so that's what's handy about having your journal be kind of transparent. Cur next equals prev equals cur, and then cur equals temp, and at the end head is going to be equal to prev, and return head. Or actually, we can just return prev. That's it. That's all there is. Oh, actually, here it should be null ptr. Let's test it. Let's go. Easy, just like that. Last time I saw it was November 2024. Nice. Okay. So if you see, this is an 81% acceptance rate. Now let's do the follow-up. A linked list can be reversed either iteratively or recursively. Could you implement both? I've actually not. I don't think I've ever solved it recursively. I know how to do it, but I don't think I've actually like solved the problem recursively. I always do it iteratively because that's the way I learned. But let's do it. So for reversing it recursively, we're gonna do basically a DFS, right? We're gonna do basically a DFS. So we're gonna start here at the head, and how do we represent it? Let's write our recurrence relation, right? So we have basically reverse. Yeah, okay, let's write our recurrence relations. Yeah, that's gonna help. I'm just gonna write like that. Actually, let me just write a shorthand for this, because otherwise I'm gonna be writing here a lot. So it's gonna be reverse linked list, RLL, and then of a node, right? So what we're gonna write here is, okay, what's our stopping condition? Do we do it this way? How do we solve it recursively, actually? How do we reference the, so, okay, so I'm thinking like node, like something like it's gonna be like node next is gonna be equal to, I can't do RL of next, like that doesn't make any sense. Oh, no, actually. So we're gonna do RLL of node next is gonna be equal to node. Right? So we're okay, this is our recurrence relation. So we have the whole list, right? And we're dividing it sort of into sub-problems. So we want to make that list smaller and smaller and smaller. So we begin with the whole list. So we want to reverse this whole list. Well, for that, what we need to do is reverse this list and then point its next to myself, right? Point its next to myself. So I'm gonna point like that. So I'm gonna reverse that and then point it to me, right? I'm gonna create a pointer to me. And then to reverse, I'm just gonna do this. To reverse that portion, we're gonna take this and then reverse it and then point it to 2, right? And so on and so forth until we get to a single node. How you reverse a single node? Like that you just it's just itself, right? So when you get to itself, then this dot next, which is currently null, is gonna become is gonna point to here, and then this dot next is gonna point to here, and then this dot next is gonna point to here, and it's gonna reverse all of them. The only one that isn't gonna be reversed is this one. So at the end, it's gonna look something like this. At the end, it's gonna look something like this. Boop, 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 and then boop instead of pointing to null. So we just have to do whatever. So we just have to do. So we fixed this because we don't want to write like another helper function. We could, but we just want to keep it really simple. We're gonna say node next is equal to null. So we point all the rest of the list to me, and then I make my pointer null. And then my child, my predecessor, is gonna point myself to it, and then it's gonna make itself null, and then so on and so forth. It's just gonna do that. Okay, so this is a way more succinct solution. I've never written this before. Okay, let's write, I'm gonna copy this. Yank a paragraph, no. Yank, where's the percentage sign? Okay. Yank percentage sign. That just copy, okay. Yank, nope. Percentage, not that one. Percentage sign, yank, there we go. And now we're gonna paste that down here. So this is gonna be reverse list recursive. So I'm just gonna create a comment here. Iterative solution. Recursive solution. Very simple. Instead of writing that, you just write what I wrote, which is, let's go back to here. There's gonna be reverse list of node next, not node next, it's gonna be head next, right? Next is gonna be equal to node, to head. And then head next is gonna be equal to null PTR. And then we're gonna reach, I missed that there, but we're gonna return the head. There is a problem here, and is our base case. So remember we said that the base case was when we had one node. We could receive a head, like a linked list that has no nodes, and if we do that, head.next is gonna get an error, and this is gonna get an error. All of them are gonna get an error because null doesn't have a next. It's null. So we have to say if head equals null PTR, return head. So that doesn't happen. So when we get an empty list, we just return it. And then that we can do that for this, right? Because when we also have to check if it's only one element, because when we get here and then we do reverse list of head.next, reverse list of null, it's gonna return itself, and then .next it's gonna get us an error. So it's gonna be like, this is what it's gonna return, and then you're gonna try to do .next, but this doesn't really work. So before we even do that, we have to say if head do we do first no and then if head next equals no? Oh, we can just do that. Well, here we can do a condition. So if head next does not equal no, then we can reverse the next one. Otherwise, we don't have to. And then we head dot next becomes null, and we return head. Okay, so we're handling two cases here. One, the list we receive is empty. If so, just return it as is. Don't try to reverse anything. Next, if we just have one node, then you're not going to reverse the next, right? You can't reverse null. So only do it if it's not null, then you reverse. Here we already know that we have at least one node, so we're gonna make the next null. This might do nothing, but it's fine. And then we return head as is. So if we have more than one node, we reverse the rest of the list. Otherwise, we just return it. Perfect. Which, now that I think about it, I think we can just do this. If head equals null or head next equals null, then we just return that. Otherwise, we reverse the rest of the list and then head dot next equals null, and then we return head. Okay. Let's copy the solution. Didn't work. Oh, we have to update the head. So we do need okay. So we do need a helper function, I believe. Okay, let's do a helper function, why not? So this is actually so we're gonna call this reverse list recursive, and it's gonna do list node head and then we're gonna have list node cur. And so all of the operations are gonna be with head. Sorry, with cur. Except, no, actually this is fine. In this case, head is gonna be equal to cur, and then we return cur. The rest is gonna work the same. except we're gonna do everything with cur. What we're doing is basically we're doing the same thing, except we're gonna keep the final head inside this head document, and we're just gonna use cur. And then reverse list. We have list node head. We're gonna do list node cur is gonna be equal to head, and then we're gonna do reverse list recursive. We're gonna pass head, we're gonna pass cur, and then we're gonna return head. So it uses cur to reverse the whole thing. Once it gets what should be the tail, it puts it in head, and then that's what we return. This is a weird song. Anyway. That is not properly indented, but still doesn't work. Oh. Reversed list recursive. And then we pass head and cur on next. Bum, 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 bum. Why am I getting one at the end? Cur is equal to head, we pass both, and we return head because this should be modified. It should go 1, 2, 3, 4, 5, and then put it at 5. Okay, let's do cout cur val. If cur cout cur val. std out is 5. It's not changing it. Am I misremembering? You think I need to do this? Maybe. Okay, what if I pass the actual thing here? Constless node. Which is just the address. What if I do that? Indirection requires pointer operand. I mean, this is not gonna work. It's the pointer of the pointer. Yeah. I just don't know why it's not getting updated. I think I'm missing something related to how pointers work that I don't remember quite well. Oh, okay, now this doesn't work. Okay, what if we do the other way around? What if instead of returning, then we need to return reverseless recursive? And we're gonna have the same problem. We're getting 5-5. See out cur val, and then head val. It never changes. War never changes. Even though here, like, did change. Okay. What happens when you pass a pointer to a function? C. It receives a copy of the pointer, changing where the pointer points. Inside the function, we'll change the... I need to do a double pointer. Yeah. Yeah. Okay. So... we're doing a double pointer. And then here we pass like the address of it, I think. Member reference of base type list node is not a structure. That's fine. Okay, that's a good refresher on pointers. Good to know. There you go. So let's copy this. And then paste it here. Delete that. And that is our solution. Okay, good to know. You need a double pointer to modify the address of the pointer within a function. Otherwise, the address is just passed as value. Base case. Recurrence relation. And then let's note here, use stem to not lose reference of rest of LL. Order of operations is very important to not lose reference to rest of LL. Okay. I want to see the iterative solution. This is locked. Sorry, no, the recursive solution. Wait, you can do it with just one function? New head is going to return itself. Wait, it's going to return the new head? Head next equals head. Oh, okay, it's I see. Well, I mean, that works. Yeah, so basically what it's doing here different, it's getting the next element through this. And actually no, it's getting the last element possible with this. Then it's just reversing its link, and then it's making, like it's reversing the links of the next element. And then it's making the its next no. Yeah, it's basically doing the same thing we did, it's just a little bit different. Well, the more you know. Okay. So we'll mark that off the list, and then validated binary search tree. Why the hell are these buffers open? Anyway, validated binary search tree. Given the root of a binary tree, determine if it's a valid binary search tree. A valid BST is as follows: the left subtree contains only nodes with keys strictly less than the node's key. Right subtree only with keys strictly greater than the node's key. Both the left and right subtrees must also be binary search trees. Okay. And this is the signature. All right, so let's see a binary search tree. A binary search tree is, let's say we have here 3, and then 2, 1. It's a binary tree, so for binary trees you only have 2 children, left and right. This is gonna be nothing. It actually just doesn't have a right child. And then here we'll put 4, actually 5, 4, 6. And so recursively what you have to do is check so okay, let's do the base case. Base case is just a single node, because when you're doing trees, most of the time you're gonna do recursive algorithms, right? Most of the time you're gonna be doing recursive algorithms because of the way they're built. So let's do our base case. Our base case, which is just a single node, it's always a binary search tree, because it has no left subtree, it has no right subtree, so obviously the left subtree is less, and the right subtree is less, and the left and right subtrees are also binary search trees, just by definition. Like an empty tree is a binary search tree. A single node is a binary search tree. Now let's go to 2. Or actually, let's do it from here. So these are both binary search tree because it's just a single node. Now we check here. Is the left subtree all of the elements less than 5? Yes. Is the right subtree all of the elements bigger than 5? Yes. Are they both also binary search subtrees? Yes. Then we go back. And well, this holds true for all of these. Now you have to keep something in mind, and that is, what if we had what I had before, which is, let's do maybe, I don't know, like 6 or like 5 here, and then you have 6, and then you have 4, and then here you don't have 6, you have 7. Here, if you just do a check of like, oh, it's my left element less and then my right element bigger, then it's always going to hold true, but this is not a binary search tree. Why? Because if I draw this 5, right? Because 4 is to the right of this tree, but 4 is smaller than 5. So this condition doesn't hold true. So we need to check 2 conditions. 1, left less, right bigger. Actually, it should be the other way around. Yeah, no, left less than root, and right bigger than root. And then we also have to check condition number 2. And this is left subtree and right subtree, not just the left and right nodes. And condition number 2, left subtree equals BST, and right subtree equals BST. To see this condition, to like check if this condition holds true, you need something. You need to find in the case of the right subtree, what the biggest element in the right subtree is, and in the case of the left subtree, in the case of the right subtree, what the smallest element in the right subtree is, and in the case of the left subtree, what the biggest element in the right subtree is. And then also, that you can use that to check this, because if you check your left subtree is less than than your root, if the the minimum element in if the maximum element in your left subtree is less than the root. If so, then that holds true. Your right subtree is bigger than your root if the minimum element in your right subtree is bigger than the root, right? So that's how you check. Now, how do you find the minimum element? You basically just, the minimum element, you just do a DFS from the root, where you always take the left path whenever you can. Yeah, you take the left path until you get to a leaf, right? So the minimum element in this tree is, you do a DFS just moving left. So you do 2, 1, and then you get to a leaf. This is the minimum element. The maximum element in the subtree is just moving to the right. This is the opposite. 1, 2, 7. Let's do it with this one. 4. Let's do it with this one. 7. Like if you keep moving down the left subtree, then you get to the minimum element. If you keep moving down the right subtree, then you get to the maximum element. That's how you find the minimum and maximum elements. And this is just doing like a recurrence relation over check. Okay, so we're gonna create two helper functions to find one to find the maximum element in a tree and one to find the minimum element in a tree. Okay. Let's not do that here. So we're gonna do vim tree. Why is this not auto-completing? Oh. Wait, did I commit? Nope, I didn't commit my contest stuff. Okay. So vim tree, and then the problem is 98.cpp. Let's copy this. And now let's create the helper functions first. So this is going to return a tree node, a pointer to a tree node, and then it's going to get min element tree node root if not root, if root is null, or not root next, or if it's a leaf node, return root. Otherwise, return get min element of root left. Just move left, move left, move left, move left until it's a leaf or an empty element. Same with the max. Nope, not what I meant to do. CTE get max element. Same thing here, but we're gonna say get max element of root right. Right? Now we have these two helper functions. Now, if get, okay, so first, if root left, if we have a left subtree, and get max element of root left, you know what? I'm always gonna assume that I'm not gonna receive a null root. So let's do that, and then we're just gonna return actually just the element. This is gonna make our job easier. So this is actually not gonna return that, but it's gonna return int. Let's do the same change here. Okay. So it's going to return an element. So get max element of root left. If that element is... We're just going to do if this is false. So if get max element is... Can't be the same because they have to be unique. Strictly less than. Ah, okay. So bigger than or equal to root. We return false. If we have a right subtree, if we have a right subtree and our get min element of our root dot right is less than or equal to a root. So if the minimum element of our right subtree is less than or equal to a root, then we return false. If those conditions hold true, then we have to do the second check. Is our left subtree a BST? Is our right subtree a BST? So we're gonna, otherwise we're gonna return is valid BST of root left and is valid BST of root right. So if both of our left and right subtrees are valid BSTs, then we return true. Now we need our base case here. If not root or it's a leaf, in which case root. I forget this is not a linked list, so not next. There's no next. If there's no root left. And here if there's no root right. So if we have an empty tree, or if we have a leaf, and a leaf is represented because the left and right are, and the left and right are both null. So if it's an empty tree, or if it's a leaf, which is this condition, then we return true. Right? Okay, this should be good. Val. Comparing pears and apples. Accepted. Resubmit. Pure cinema. Well, this is very fast, but I guess there is an optimization you could do, but you kind of have to exchange it for memory. One of the problems of what we're doing here, one of the inefficiencies, is for every node, you're calculating the minimum subtree, so that the minimum element of the maximum element of the left subtree and the minimum element of the right subtree. And sometimes that element, that minimum and that maximum doesn't change. Right? If I'm here, my maximum is 7. If I'm here, my maximum is still 7. If I'm here, my maximum is still 7. As long as I keep walking the right subtree, my maximum is going to stay the same. The same holds for the other way around, for the minimum. If I'm here, my minimum is 1. If I'm here, my minimum is 1. If I'm here, my minimum is 1. When does it change? Let's say we have 3 here. And actually, this should be... I'm going to create a correct... Okay. When does it not hold true? Let's do our maximum again. If I'm here, the maximum is 8. If I'm here, the maximum is 8. If I'm here, the maximum is no longer 8, because 8 is no longer in it. It's now 6. And if this had any like things in here, then the what? the maximum would stay the same if you kept moving the right subtree. And at the point where you start moving the left subtree, the maximum changes. You have to recompute it, right? So you could do some way to like store the maximum and like reuse it, but then you're trading memory for efficiency, right? Because you need some way to store that minimum or that maximum and reuse it when you don't need to recompute it. And actually, this doesn't really matter for these types of problems, because if you think about it in like terms of like efficiency, because if you think about it, the time complexity of computing the minimum or maximum is log n, because you're walking from the top to the bottom, right? And that is equal to okay, no, this is actually not true, because it's only log n if it's balanced, but let's assume it's balanced, right? Computing it would be log n, because in a balanced tree, the amount of floors, or the amount of levels, I guess, is log n. This does not hold true if your binary search tree looks like this. So at that point, it's just a linked list, so walking this is O of n. But how big are our elements? Like, what's our number of elements? 10 to the 4. So even if we do n, not very expensive. Do we get told this is a balanced binary tree? No. Well, in this case, it passes because they're not focusing on this. But in a better solution, because normally time efficiency is more important than memory. It says, "Hey Ed, is this chat visible? Appreciate the grind. Thanks, man. Sorry, I just saw your chat. It was 3 minutes ago. I don't know if you're still here, but thanks for watching. So what I was going over was, in a perfect solution, since this tree that they give you doesn't actually change, you can compute the minimum and maximum for all of the elements. There has to be, I don't have the algorithm, like I can't spit it right out of my head immediately, but there has to be an algorithm to find the minimum and maximum of all the elements in like efficiently. It should be O of n for each of your elements, something around those lines. And then if you have the minimum and maximum of all of these, then you can just use them for the algorithm. So you can pre-compute them since your tree isn't going to change. But in this case, it doesn't matter. Like, it's 10 to the 4, so our final time efficiency is going to be... Okay, so we're checking every single node to check if it's a BST. So that's n. And then we're calculating the minimum element for every tree. So that is log n if we think it's balanced. If we don't think it's balanced, then this is n in the worst case. Like, if we think it's something like this, I don't know. I think it ends up being like amortized, and it doesn't end up being that expensive because O of n squared might not fit in this problem, being 10 to the 4. Let me think about this. If we have a tree like this, right? Our minimum over left is going to cost us O of n, and this is going to cost us... So it's going to be 1 plus 2 plus 3. So that's O of n squared, basically. Yeah, so this is O of n squared in this case. Because when you're getting the minimum element here, it's 0. Then you're getting the minimum element here is 1. Then here is 2. Then here is 3. So it's 1 plus 2 plus 3. This is equal to a summation of I equals 1 until n, which is equal to n times n plus 1 over 2, which is equal to O of n squared. So yeah, it doesn't actually end up it ends up being O of n squared if the tree isn't balanced, which I think still fits within the problem, but it's something to think about if the constraints were different. If the constraints were different, you want to pre-compute all of the minimums and maximums and then actually do this. In that case, it would be O of n, I believe, because pre-computing all the minimums and maximums should be around O of n. And then you do this whole algorithm with these pre-computed, so it would be O of n times 1. So you just do 2 times O of n, which is O of n. But anyway, let me just write up the documentation for this, and I'll call it a day. Idea. 2 conditions for a tree to be a BST. I'm just gonna copy this. Well, actually, the 3 conditions, actually. Well, no. Let's just say 4 conditions and divide them up. The minimum element in the right subtree is bigger than root. The maximum element in the left subtree is smaller than root. The left subtree is a BST. The right subtree is a BST. And let me check my assumptions. Why do we need to check for this? Let me provide a counterexample. Let's say we have the same 5 here, and then we could have 1, 3, 2. And then the right subtree here doesn't matter. Let's say it doesn't have one. So in this case, the maximum in the left subtree is 3, which is smaller than the root. So this is a BST. However, this is not a BST because 3 is bigger than 1. And 2 can go here, but 3 is bigger than 1. So this is a problem. So therefore, the whole tree isn't a BST. Okay. Left tree is a BST, and right subtree is a BST. Find min element in a tree by walking always left. Vice versa for right. For finding max. Actually, not vice versa. It would be the reverse for finding max. The right for finding max. And then yeah, we're basically just doing that here. Okay. Looks good, sounds good, feels good. Get status, get at period, get commit minus m. But this is the console logs 21. All right. Okay, well, thank you guys. That's it for me today. We solved our two LeetCode problems of the day. We talked a little bit about what was it? Content aware storage. We talked about oh, I haven't talked about what's going on this week. Actually, I think I did. But anyway, I'm just gonna um recap. Basically, a Thursday we're gonna keep working on the C Sharp agent research agent RAG agent project, and then Saturday I'm doing another LeetCode contest. So tune back those days if you're interested in looking at that. And otherwise, I'm gonna log off. Thank you all for joining. I appreciate the support. Thank you, Tanish, for coming to the stream and sharing your support. And I'll see you guys on Thursday.